Hello everyone, welcome to Sri Chaitanya Academy, and let's start this chemistry session where we are going to start a brand new concept of redox reactions. Redox reaction, where red means reduction and ox means oxidation. Right? So in this redox reactions, the first thing that we have to define in order to understand redox reactions is oxidation number. So what is oxidation number? Well, in redox, mostly, I'll give you a small idea that oxidation in redox means loss of electrons, okay? And reduction means gain of electrons, right? So what we do is we take a compound, a covalent compound, mostly. If B is more electronegative than A, then B pulls these electron shared pairs towards itself, right? And gets a number of -1. And because A donates, it gets a number of +1. So what we are assuming is that this lone pair has completely shifted on B, giving it a -1 charge, and it has completely left A, giving it a +1 charge. So this assumption that this lone pair has completely shifted to B gives us a ionic state of this atoms, right? The charges on these atoms in that state are called oxidation number. So now let's get to the definition. Oxidation number denotes the oxidation state of an element in a compound ascertained according to a set of rules. Set of rules? Yes, we will discuss those set of rules. Formulated on the basis that electron pair in a covalent bond belongs entirely to the more electronegative element. So this is shifted. Let us take an example. You have HCl, right? So chlorine is more electronegative. We learned in the Pauling electronegativity scale that Cl is much more electronegative than H. So these electrons are assumed. Remember, this is an assumption. This is not the reality. This is not reality. Reality is this, right? So when you shift them here, H will get a +1 charge, -1. These are the oxidation states. So oxidation state or oxidation number, both are same, right? Now the rules, right? Rules. The oxidation number of an element in its standard state is always 0. What is this standard state? It is state in which element exists under normal conditions. Under normal conditions, right? Under normal conditions, whatever it is there, for that the oxidation state is 0. So what I'm trying to say is here for hydrogen. Now remember, oxidation number is always of an element, or I should say or atom. It is never defined for a compound or a collection of atoms. So whenever they ask you oxidation number, remember they're asking you of a single atom, a single type of atom or an element, right? So, right. So here oxidation number of hydrogen is 0, right? Similarly, if you go to any of these compounds like oxidation number of iron, 0, right? So, right. Next is alkali metals. Alkali metals are which? It is the first period, right? Which one is? Remember that alkali metals can exist, can lose a single electron, right? All of them can lose a single electron like this, to form this, right? So this is this. So alkali metals always have a +1 oxidation state, +1 oxidation state, right? Moving on, alkaline earth metals. Now these are the group 2, right? Group 2 metals, which are understand that all of them can lose 2 electrons, right? To give you di-positive cations, right? Di-positive cations. So all of them have an oxidation state or oxidation number of +2, because +2 is the charge on that metal, right? Now oxidation state of H attached to an electronegative atom. Can you think of an example of H attached to the electronegative atom? Well, tell me an example of where hydrogen is attached to an electronegative atom. Tell me that example if you can. The best example is, and the best known one is, HCl. We know that chlorine is more electronegative, right? So chlorine will get a -1 oxidation state and hydrogen will get a +1 oxidation state. So when this happens, oxidation number of hydrogen is +1 in the positive sides. Now, when the same hydrogen is attached to an electropositive element, electropositive elements are what? Those are your metals, right? Now, this basically happens in metal hydrides. So, if you have metal hydrides, then you will get that, like sodium hydride or magnesium hydride. So when you have these things, you will get that. Why this happens is because the metal is capable of losing electrons much more easily than hydrogen, and it is lost. This gets a +1, this gets a -1. So understand that these rules are just a way of telling you. The most basic thing is check which is the more electronegative element and put a -1 on that, right? So here out of these two, hydrogen is more electronegative than sodium. So you'll put a -1 here. So the oxidation number of hydrogen will be -1, right? Moving on. Oxidation state of oxygen attached to less electronegative atoms. Now talking about oxygen. Now can you give me the most used example of compound of oxygen, which is present, which is the most abundant compound on earth? Which is the most abundant compound of earth on earth? It is water. So when you have a compound and you're confused what should be the oxidation state or the oxidation number, what you should do is write down the structure. So if you write down the structure like this, then life will be little easy. How the life will be easy? You see, every time to calculate oxidation number or oxidation state, concentrate on a particular bond. Suppose you concentrate on this bond, right? In this bond, check which is more electronegative. Oxygen is more electronegative, right? Clearly, right? So for this single bond, put a -1 here and a +1 here. Next, move your attention to the other bond. Now in this other bond also, you see oxygen is more electronegative, so put one more -1 here. And here you put +1. So -1 -1 adds up, giving you -2. So oxidation number on oxygen here is -2. Understood? So this method if you use, you will always get the correct oxidation number or the correct oxidation state, right? Let us take some more example, like this one will come to next. Now, when O in oxides, now O in oxides, what do I mean by that? suppose you have, let us talk about oxides first. So let me have calcium oxide. Calcium is the alkaline earth metal, +2, this will have -2. So in oxides, the oxidation number of oxygen is -2. No surprises there, right? Mostly oxygen's oxidation number will be -2 only if it is attached to less electronegative element. But if you talk about peroxides, there is something called peroxides which have this linkage. This linkage is called the peroxy linkage, right? Peroxy linkage. Now, the perfect example of this is HOOH. This is called hydrogen peroxide, short written as H2O2. It is not water, remember, there is a 2 here. So it is H2O2, right? So in this hydrogen peroxide, what you can do here? Follow the same rule. How will you find the oxidation state? Concentrate on one bond at a time. Concentrate on this bond. If you concentrate on this bond, out of hydrogen and oxygen, which is more electronegative? Oxygen, so put a -1 here. Now move to the next bond, oxygen and oxygen. Both now have the same electronegativity here. If you get a bond where both atoms have the same electronegativity, then do not consider any oxidation number. So it is nullified here. Here if you go, again the same situation. So now I am going to ask you the oxidation number of this single O atom, of any O atom. So here the oxidation number of O will be -1. Remember, now it is about an atom. Do not add these oxidation numbers and give -2 here. No, the oxidation state of one atom you are talking about, always one atom we will talk about, that is -1. Right? I think that is clear. This is called peroxide. Like this, you can also have many other peroxides. So this ion will be how? O2 minus, right? So like this, you can write this ion, right? O2 minus, and you will have many like this, Na2O2, right? You will have MgO2. Right? So like this you will have many peroxides. Now after peroxides, let us go to the next part, which is your superoxides. What are superoxides? Simply, see, peroxides is O2 minus, superoxides are O2 single minus. So what do I mean by that? Simply, 2 oxygen atoms are there and each of them have a -half. So the oxidation number here is -half, right? So those are superoxides like NaO2, KO2. These are superoxides. So oxygen can have a number of oxidation states based on what kind of oxide it is in. Now, when oxygen is attached to a more electronegative atom, so can you tell me an example? More electronegative than oxygen is only one, fluorine. So OF2. So you have F. Fluorine is more electronegative, so -1 it will get +1. -1 it will get +1. So now if you on the same atom, see, if on the same atom a charge is there, then you can add. But if it is on, sir, only one watching. Okay, no issues. Even if one is watching, right, that one should understand that is my purpose, right? Right. So +1 and +1 makes it +2. So the oxidation number of oxygen here is +2, not minus, specifically in here. If you remember, I told you that fluorine is the most electronegative, then oxygen, and then chlorine. Okay. Now, if the compound is OCl2, then things will be different. Why? Because now oxygen is more electronegative again. So -1 here for this bond, -1 here for this one bond also. So this will again be oxidation state of oxygen will be minus 2, right? And this will get plus 1, right? Now, next, oxidation state of halogens. Oxidation state of halogens when attached to more or less electronegative element, right? So, how do you calculate the oxidation state of halogens? Halogens are, if you remember, fluorine, chlorine, bromine, iodine, right? Now, so they're talking about, well, attached to more or less. So let us take an example of less electronegative element. So one is HCl. Hydrogen is less electronegative than chlorine, correct? Right? Because hydrogen is less electronegative than chlorine, it will easily give its electrons to chlorine and it will get -1, this will get +1. So now the chlorine's oxidation state is -1. But on the other hand, if I change this, remember, if I change this to something else, this. Now, oxygen is more electronegative than chlorine. So, oxygen will pull electrons to -1s and chlorine will get +1, right? Same way you have IF7. If you want to calculate the oxidation state of iodine here, understand that IF7 6, right? So for each bond, for this single bond, this will get a, fluorine is more electronegative, right? Fluorine is more electronegative, so it will pull. So -1 on each fluorine. And for each -1 on each fluorine, there will be a +1 on iodine. So how many +1s on iodine? How many +1s on iodine? People, just tell me in the comment section. How many +1s you will get on iodine here? There are 7 fluorines. The +1s will be +7. Total will be +7. So the oxidation state of iodine will be +7. Right? So in this way you can move around oxidation states. Now oxidation states of cations and anions. Now this is particularly easy. You know that Na+, the oxidation state is +1. Yes, oxidation state can be 0, negative or positive. Anything it can be. Like this oxidation state is -1. Or if I ask you in this compound, oxidation state of hydrogen, that will be, remember, oxidation state or oxidation number, I am repeating again and again, it is only for a atom, a single atom, an element, 0, right? So cations and anions, you have a complete list of cations and anions which you have studied in your lower classes. You can take them up, from there you can get your oxidation states. Now, one thing, suppose I have this anion. So can we find the oxidation state of manganese in this? Please, I am giving you a little time, just try it out. Oxidation state of manganese in MnO4-. This minus, remember, when in a group this minus is written, this minus is on this complete molecule. It is not only on this oxygen, it is on this complete molecule. It is something like this, okay? So try and find out the oxidation state of manganese. Now, to get to this, we will use some maths, basic maths, nothing big. Let the oxidation state of manganese be X, right? X be the oxidation state of manganese, right? Let it be X. Now X plus. Now each oxygen here will have an oxidation state of -2, right? It's an oxide, it is not a peroxide or anything. Remember, peroxides, superoxides, you will be able to see them clearly. Normally oxygen has a -2 oxidation state. So here 4 oxygens are there. So the charge will be -2 oxidation state on each oxygen multiplied by 4. Now the total charge is -1. If you solve such an equation, you will get the value of oxidation number on manganese. How do we do that? Let's see. This comes out to be -8 -1 x equals to, this -8 goes to that side, +8 -1 x equals to +7. So the oxidation state of manganese here is +7. You can write it down like this on top of manganese, right? So let us take some few more examples of this type of a calculation because it is important. So let me take that. Let me take a new slide as well for that calculation, right? So next, use SO4 2-. Everyone try to find the oxidation state of sulfur in this. Try it out, whoever is watching, right? Try to find out the oxidation state of sulfur. Start by letting it as X. One sulfur is there, so for that sulfur you put X plus. How many oxygens? 4, right? So each oxygen has a -2 charge. There are 4 here, and the total charge on this complete anion is -2. Correct? So now let it go that side, +6. So you'll have +6 oxidation state on sulfur, right? Okay. This one, let us try. Now here understand that there are 2 chromiums, right? I am now going to ask the oxidation state of chromium, right? No, +2, no, it is +6, right? In chromium, so I will now take, because of single chromium atom, the oxidation state is X. Of Cr2, it will be 2X, again 4 oxygens. I think next it is self-explanatory. It goes there, it becomes so oxidation state on chromium here is +3. So like this, you should be capable enough of finding the oxidation states of a particular atom in a particular compound, right? One more, let us take. Let me just erase the previous one. Okay, let us take it here. I'll change the color. PO4 3-. Find the oxidation state of phosphorus here. PO4 3-, the oxidation state of phosphorus. Try it out, whoever is there, 4 people are watching. Please, this topic I already know. If you do not have a notebook in front of you and you are not using a pen, then my dear friends, you will never get this, right? Now chemistry has moved on from just being a subject which you can just read and memorize and vomit it out in the paper. You have to be able to solve. All chemistry, maths, physics will intermingle in every aspect of the subjects. So take out your notebook, take out your pens and start scribbling, start writing down and start solving. Only then you will get a answer. Tell me, PO4 3-, the oxidation state of phosphorus in this. What is the oxidation state of phosphorus in this? Phosphorus, you will let it as X, right? each oxygen, minus 2, 4, total charge is 3 minus. Remember, this 3 minus is on the total thing, not only on oxygen, right? Right. Yeah. Thank you for attending as well. Just pay attention and keep solving. Solving is important. So minus 8, minus 3, take that to that side, plus 8, minus 3, plus 5. This is plus 5 state. Remember, this is the oxidation state or the charge on phosphorus. Now, this is not the actual charge on phosphorus. Remember, oxidation number, I should not forget this. This oxidation number which we are writing, this can be an real or it can be imaginary. Okay. So, real is when it is real. In what case? Here it is real. It is a real charge, right? Real charge of plus 2 is there on magnesium. But in this case, this is not real charge, right? There is no charge on oxygen as such. It is just for our satisfaction, and you will see that as you move on and we do reactions, there this helps us in telling whether oxidation or reduction has occurred, right? So this is your imaginary. This is an imaginary charge. So whether it is real or imaginary charge, imaginary means not real, it is still called the oxidation state or oxidation number. So keep this in mind. I forgot to tell this point, so that's why. Now here also, here also it is a imaginary. Right. So this is something which we have made up just for our convenience, right? Why we have made this up? Well, that you will understand as you move forward. So now, the next is when you have a coordinate bond. I have taken two examples. So you have H, C. Right. Here, the third bond is a coordinate bond. What is a coordinate bond? Nothing. Both the electrons which are there in this bond come from this carbon. Right? You will learn more about it. Now, when this coordinate bond or when a bond is pointing, if the electron donated is by an less electronegative atom, if electron is donated from less electronegative atom, carbon is less electronegative than nitrogen, that is pretty clear here, right? To a more electronegative atom. This is more electronegative. Then for each this kind of a bond, if there is one bond, then once, if two bonds, two. For each of this kind of a bond, you will put on the atom which is donating plus 2 oxidation state and the atom to which it is donated minus 2, right? But if the situation is opposite, how is it opposite? It is in HNC. Now, this is the coordinate bond. Now, the donation is happening from more electronegative atom to less electronegative atom. Then, forget about the bond. No need of thinking anything. Just forget about this bond. There is no contribution. No contribution to oxidation state. Now, as an exercise, now this is just for this single bond. You have what? You have two more bonds. Now, two normal bonds will give you how many? For this one bond, you will get plus 1 here. For another one bond, you will get another plus 1. Right? On nitrogen also, you will get minus 1 for one bond and minus 1 again for the other covalent bond. Total you will get here minus 4. Here you will get, no, there is one more bond here. First of all, every bond you have to calculate. So here you again get plus 1 for this one. sorry, carbon is more electronegative than hydrogen, so you will get a -1 here for this hydrogen, here you will get +1. So on carbon, the total oxidation state is 3, 4, -1 plus 3. This has an oxidation state of -4. If you come to this one, pretty simple, hydrogen, nitrogen, nitrogen is more so now for these two bonds you have to consider, this bond you have to ignore. If you do that, then what you will do, nitrogen is more electronegative, so -1, -1, this becomes -3. Here it is donating 2, so +2, right? Coordinate bond, what it is, how it matters, you will get to know it when you move forward, right? A coordinate compound chapter is there. There this point will be useful. Moving on. Now, you remember this method of calculation which I have discussed till now. This method of calculation is useful. Yes, it is useful if you do not know the structure. But through this, sometimes this calculation fails. When does it fail? Let us go to this. Right. Now, if you, through the same calculation, try to find out the oxidation state of chromium here, let us get to that. So, X for chromium plus on each oxygen -2, 5 are there, and total charge on this is 0, right? If that is the case, X -10, 0, X equals to +10. So the valence shell, this also you will understand, valence shell of chromium, in the periodic table chapter, I have told you chromium is 3d5 4s1. So the valence shell has 6 electrons. Now understand that +10 means how many electrons has chromium donated? 10. Is it possible? Valence electrons are 6. So maximum oxidation state possible is how much? +6. What is this +10? It means that we are wrong. Why we are wrong? Because maximum it can donate. See, if you have 10 rupees, if you have 6 rupees in total in your pocket, you can only spend 6, right? You cannot spend 10 rupees. That is the thing. If you have 6 electrons in your valence shell, you can only donate 6, you can't donate 10, right? So there is something wrong. So this does not work here. For this special cases, you have to go to the structure. Now, what is the structure? Focus your attention here. The structure is somewhat like this. We call it the butterfly structure. Because it looks like a butterfly. Now we are going to use our basic, that bond by bond we are going to calculate what oxidation state it can have. Out of chromium and oxygen, suppose this bond I am concentrating on, out of chromium and oxygen, which is more electronegative? Oxygen. So oxygen will get a -1 here, chromium will get a +1 for that oxygen. Similarly, it will get +1 for this, this and this oxygen, right? So you will get 4 +1s. Right. What about this oxygen? Understand here, this is a double bond, 2 bonds. So for this one bond, it will get 1 +1 here. For the other bond, it will get another +1 here. Okay. And this oxygen will get -2, right? Here chromium got +1, oxygen will get -1. Here also -1, -1. So how many +1s does the chromium have? People count it out. Please count how many +1 the chromium has. Whoever is watching. How many +1 the chromium has? Tell me. Look at it. In the comment section, please tell me how many plus ones does the chromium have? The chromium metal atom have. A simple counting, you can see through your eyes, right? If you are actually attending this session, please give me an answer in the comment section. I'm waiting, everyone. Whoever is watching, how many plus ones the chromium has? Okay. See, like this, attending will not give you anything. You have to give an answer. How many? In the comment section, please type it out. How many plus ones does the chromium have? Okay, no answer. Right. Since it is a timed session, we don't have a lot of time, so I'll give you an answer. Simple addition also. 1, 2, 3, 4, 5, 6. Right? So the chromium oxidation state is plus 6, which I had easily predicted based on the valence electrons. Right? Chromium has 6 valence electrons, so plus 6. Now here oxygens have a different kind of oxygen has a different kind of oxidation state. Like these oxygens have -1, this oxygen has -2. So sometimes it is important to write the structure and then get the oxidation state. Next, you have the Carr's acid, H2SO5. To understand this structure, let us write the structure of H2SO4. This is the structure of H2SO4. To write H2SO5, let us add one extra oxygen we need, right? So how do we do that? Simply add that oxygen here. This is your H2SO5. Now simply use bond by bond movement to calculate that now. Focus your attention on this oxygen. In this oxygen, one side is hydrogen, other side is oxygen. Out of oxygen, hydrogen is less electronegative, oxygen is more electronegative, clearly. So this will get a -1 for this bond. For this bond, it will not get anything. Why? Because both have same electronegativity. Out of oxygen and sulfur, oxygen is more electronegative again. So oxygen will get -1, but sulfur for that will get +1. Correct? Right. Now, again moving forward, for these oxygens, each are having 2 bonds. For each 2 bonds, you will get +2. For here also, you will get +2. Oxygen will get -2, -2. For this bond, you will get sulfur is less electronegative, oxygen is more, so -1 here for this and a +1 for that. And even in this bond now, oxygen is more electronegative, -1 here, +1 here. So like this, you should be able to find. Now what is the, add this up, the total oxidation state on sulfur, 4, 5, 6, +6. So sulfur has +6 oxidation state in Carr's acid. Next is Marshall's acid. These are specific examples, don't get worried, right? H2S2O8. Again, I will start with something which we know already, H2SO4. So H2SO4, if I take 2 H2SO4, right? See, S is twice, O is twice, right? 4 plus 4, 8, S plus S2. Only this hydrogen is extra, right? Hydrogen is extra. So what to do? Write the structures first. So you have to remove 2 hydrogens, right? That is clear. So nothing. What are you waiting for? Remove the 2 hydrogens. Remove these 2 hydrogens out of the picture. Minus H2. you will get Marshall's acid formula. Now, bond by bond movement is what we need. Let's do that. For sulfurs, for this oxygen, sulfur will get -1. For this oxygen, because two bonds are there, sulfur will get +1 because oxygen is more electronegative. For this oxygen, single oxygen, you will get +2. For this single oxygen, again you will get +2. For this oxygen, you will get +1. You will get +6, right? So this sulfur has +6 oxidation state here, because this is same as this, +6, right? This is your Marshall's acid. People who are just joining in and leaving, you will not be able to understand anything because you did not attend the previous sessions. Tetrathionate ion, S4O6 minus. It has a little bit tricky structure, right, like this. So there are two different kinds of sulfurs here, right? Let us get to that. Sulfur, sulfur, same electronegativity, so 0 oxidation state. Oxygen, 2 bonds, for each bond +2. So +2 here, +2 for this, and for here +1. So this sulfur is +4 oxidation state. This is also +4 oxidation state, and these two are 0 and 0. Moving on, bleaching powder. Like this. Now this is the structure of it. Yes, you have to remember the structures. This is calcium. Out of oxygen and calcium, which is more electronegative? Oxygen. So it will get a -1 here. Calcium will get a +1. Out of calcium and chlorine, which is more electronegative? Chlorine. So chlorine will get -1, calcium will get +1. Total oxidation state here will be +2. Now, out of oxygen and chlorine, which is more electronegative? Chlorine. No, oxygen is more electronegative. So +1. So see here, in the same compound, the same atom has two different oxidation states. One chlorine has +1, the other one has -1. This is the power of structure in chemistry. Remember, try to know the structure of compounds, right? That the detailed structure, that is what is going to give you an exact answer. Moving on. Br3O8. Br. Right, 6,6, Br3O8, right. Understand that this Br has +2 from here, +2, +2, +2. So let me write that +2, +2, +2, +2, right. So total it is +6. Okay. Now here this bromine, because this bromine bond, same electronegativities, nothing will be different. So here it will get +2 for this, +2 for this. So +2 here, +2 here. This bromine is +4. Here same as this also +6. So like this, you should be capable enough to find the oxidation states. Now what is a redox process? After studying all this, let us move on to what is actually a redox process. A redox process is a process where oxidation and reduction occur simultaneously. Means oxidation is also happening, reduction is also happening, right? So there are many types of redox reactions. Now redox process, let me take an example. It's not balanced, but just understand this. Manganese oxidation state, we have already found it is +7, and here it is +2. Iron is +2, here it is +3, right? So why this oxidation number drama I did is because if there is an increase in oxidation number, it means it is oxidation. If there is a decrease in oxidation number, it means it is reduction, right? This is N, reduction. So remember, for now and the time to come, this is your guide of oxidation and reduction. If there is an increase in oxidation number, it is oxidation. If it is a decrease in oxidation number, it is a reduction. So now let's see what happens here. As you go from iron 2+ to Fe3+, what is happening? There is a increase in oxidation number, right? Increase in oxidation number. So this is a oxidation. But what is happening on the top? There is a decrease, right? +7 to +2. There is a decrease of +5. So it is decreasing. There is a decrease in oxidation number. This is reduction. And this single reaction in which oxidation and reduction both are occurring in the same reaction, this is called a redox reaction. A redox reaction, right? So everything which we have studied till now actually gets focused in this. Now let's talk about some types of reactions. One is combination reaction, right? That carbon plus oxygen combines to form CO2. Is this a redox reaction? Let us see. It can or cannot be also. 0. Here what is the oxidation state of carbon? If you take carbon as X, oxygen -2 into 2, charge is 0, X equals to +4. So here the oxidation state is +4. Oxygen here 0 because oxygen in the standard state. For this also I can tell you a easier way. Oxygen is there, charge is 0, so 2 oxygens, each oxygen is X, so 2X, 0, X is 0. Like this if you do also you will get, right? Now what is the oxidation state on oxygen here? We assumed it -2, right? So carbon, can you see? Oxidation number is increasing. So it is what? Oxidation or reduction? It is oxidation. Because increasing oxidation number is, see, that is why it is called oxidation number. If it increases, then it is oxidation. If the oxidation number decreases, it is the opposite of oxidation, which is reduction. Now here what is happening? 0 to -2. -2 is less than 0, right? I hope this you know. There is again oxidation number decreases, there is reduction. This is a combination reactions, means two things are combining to give you a single thing. Decomposition reaction. KClO3. If you heat, this is potassium chlorate. If you heat, you will get KCl plus oxygen. If you balance this out, 3/2. Again, to find the oxidation state of chlorine here, see potassium will have +1, chlorine suppose has X, oxygen, each oxygen -2, 3 are there, total charge is 0, right? Try and understand this equation very well. So this will be X -6 +1, 0. X will be +5, right? Oxygen is -2. Here it is -1, right? And here oxygen is O2 is 0. So again, is it a redox reaction? Let us check it. +5 to -1. It is reduction, right? So oxidation number reduces, so it is reduction. What about this? -2 to 0. See, -2 is less, 0 is high. So there is an oxidation number increases, so this is oxidation. So decomposition reaction is nothing, it's just that you are breaking a particular compound into smaller compounds on heating. Triangle means heating. Okay, again decomposition it is there. Metal displacement. You have zinc, copper sulfate, zinc sulfate plus copper 2+. Right. So what has happened here? Zinc has kicked out copper from this and formed this. Now here also let us check the oxidation state. This is 0. Here it is +2 because zinc 2+, SO4 2-. Now copper, SO4 2- is the same. Copper here is +2, right? Sorry, here it will not be +2 here. Just let me just remove this. Sorry. Why I am not able to select the eraser? Yeah, this is copper, sorry. 0. Right? So from here to here, what is happening? There is an oxidation number decreases, so there is reduction. Here 0 to +2, oxidation number increases, so this is oxidation. A metal is just replacing. Non-metal displacement. I am not going to balance it. So here a non-metal is getting displaced. So this is getting displaced. That displacement can be by anything. It can be a metal, but then the thing that is getting kicked out should be a non-metal. So this is a non-metal. Now this oxidation state is 0. So let us write it on top. -1. Here this is -1. This is 0. So again the same drama let us do. 0 to -1. Reduction in oxidation number. Oxidation number reduces, so this is reduction. -1 to 0. Again increase in oxidation number, so this is oxidation. Moving on, disproportionation. Now disproportionation is something different. It tells us that when from a single compound an element in a single oxidation state reacts to give a compound in higher oxidation state of element plus a compound in lower oxidation state of element. So what do I mean by this? Let us understand. Understand that this is a single compound, chlorine. The oxidation says, Lucky Prajapati, when did you join? If you have joined just now, you will not understand this. What you do is, I will explain just after the session is over. Go back and see this video from the starting. Everything is interconnected, okay? So if you see this video from the starting, the previous part will be clear, okay? Right. So in this one, this will be having a zero oxidation state, right? So here it has -1 charge, so -1 oxidation state. Here this is OCl, right? Na plus. So +1 here, -2 plus x, 0, x will be equals to +1. So here the oxidation state is +1. So understand that what is happening here. This is -1, dears. From the same compound, you're getting a compound, one of lower oxidation state and another compound of higher oxidation state. From the same compound, right? So from the same compound, you're going here, you're getting what? You're getting reduction. And from the same compound, the arrow starts, you're getting oxidation. When this happens, it is called disproportionation, right? From the same compound, when from a single compound, an element in a single oxidation state reacts to give a compound in higher oxidation state of element plus a compound in lower oxidation state of element, then that is called disproportionation, right? Now moving on, if you have covered this, written this down, comproportionation. Nothing, it is reverse of disproportionation. This previous reaction, write it in reverse. It's comproportionation. Where from what is going to happen? This is +1. Sorry, this is -1, +1, 0. From a higher oxidation state and a lower oxidation state, you go to a single oxidation state, right? So if I write from a higher oxidation state plus lower oxidation state, in two compounds, you go to a single oxidation state in one compound, right? So you can see that this is called comproportionation. Now after this, it is an end. Redox reactions are done away with. So if you like this session, then fill this Google form, whoever is there till the end, fill this Google form so that we can give you much more stuff than this and give you further updates of whatever is going to happen on the Sri Chaitanya Academy channel, right? And if that is done, also join our Telegram channel where much more than this is being shared every single day. There are questions, solutions, worksheets, so many things are there. So it is bye for now from my side. Next you have a math session, right? Get ready for that. by the time I'll take your leave.